Hi all, today we'll discuss Chapter 19, Danger in the Air, Stormy Weather. This chapter can be broken into three different sections, with the first discussing air masses and fronts, the second discussing storms, their anatomy, their formation, and their hazards, and third discussing mid-latitude and tropical cyclones. Air masses are broad bodies of air with fairly consistent temperature and humidity throughout. These are characterized by the source region and their latitude of origin. For example, here's a picture of air masses over North America, where we have continental air masses over the continent and maritime air masses starting over the oceans. And then we have latitudes Arctic, polar, and tropical. Now, it may seem confusing that the continental air mass is over the middle of the United States, which isn't exactly tropical, but I encourage you to recognize that this air mass may not have initially started in the western part of North America, and it may have started a little further south. Fronts are boundaries between two air masses, and there are several types defined below. A cold front is when cold air masses advances under warm air masses. A warm front is when a cold air mass retreats and a warm air mass advances. An occluded front is where a cold air mass overtakes a warm front so that two cold air masses come into contact with one another. And a warm air front is no longer in contact with the ground. It has been pushed up. Then finally, there's a stationary front, where cold air flows parallel and warm air rises over the cold air. So this really all has to do with the different directions the warm air and cold air are going, which we'll see in the next few slides, but I'll describe briefly now. In this picture of a cold front, you see there's a line marked by blue triangles on the warm side of the front, and it's associated with precipitation depending on the warm air ahead of the front. Notice that the directions of cold air and warm air are opposite one another, and they're crashing into each other. This is the definition of a cold front, with the warm air rising. A warm front is shown here with the line marked with red half circles positioned on the cold side of the front. Precipitation also depends on the nature of the warm air mass. But in this case, we have the warm air mass and the cold air mass moving in the same direction, but with the warm air mass going above the cold air mass. This will always be the case, that warm air rises above cold air because cold air is more dense, as defined in our atmosphere lecture. The occluded front here is indicated by the purple line, the alternating triangles and half circles pointing away from the coldest air. Cold fronts usually move more rapidly than warm fronts, and in the case of the occluded front, you get the cold air from two fronts hitting one another. I'll mention that another slide in this presentation provides a better description or a better image of the process of an occluded front forming. But in this case, as in all others, the warm air rises above the cold air. Then here we have the final stationary front, which is indicated by a line of alternating red and blue segments. The blue triangles on the blue line point towards the warm air, and the red half circles on the red line portions point towards the cold air. Weather along such front may remain for a long time. In this case, when you're looking at relative directions, you're seeing the cold air and warm air blowing perpendicular to one another. Now that we have a good understanding of the different types of air masses and different types of fronts of warm and cold air and how they interact, we can start to discuss thunderstorms. Thunderstorms generally consist of towering cumulonimbus clouds that produce lightning and thunder. Thunderstorms take place frequently in some places on Earth, but rarely occur at others. Most thunderstorms are concentrated near Earth's equator, as shown in the figure below. This figure estimates the distribution of global thunderstorms from lightning flashes, where you can see they're counted in per kilometer squared per year, with the highest regions being equatorial. Notably, Central Africa has the most thunderstorms. This is a map of the United States that shows the number of thunderstorm days per year, at least in the continental United States. The Southeast holds the record for highest number of thunderstorm days, with 65 to 80 days of thunderstorms per year in certain locations. Thunderstorms form when three conditions exist. The first is the occurrence of moist air in the lower atmosphere. This is often from ocean evaporation that blows inland from the Atlantic Ocean and the Gulf of Mexico in the case of North America. The second condition is a lifting mechanism that causes an updraft. And the third condition is an atmospheric instability that allows the air to continue to rise to the tropopause, which is the top of the troposphere. There are three types of lifting mechanisms. The first is called frontal lifting. This occurs when a cold air mass moves under a warm, moist air mass. This often triggers a line of storms along the front, shown in the figure on the bottom right, which in this case, the storms stretch from Oklahoma to Indiana. A gust front is an outflow of cool, dense air created by a downdraft from another thunderstorm. In this case, the gust front pushes the warm air adjacent to it upward and replaces it near the surface. In this picture, we have two gust fronts occurring on either side, producing the rising of warm air in the middle. The final lifting mechanism is due to warming from below. So updrafts can begin over mountain ranges when, during a hot afternoon, the slopes of steep mountains warm the adjacent air. Our third condition for the development of thunderstorms is atmospheric instability. Atmospheric instability occurs when air continues to rise after an initial lifting. Adiabatic expansion occurs when an air parcel does not exchange heat or mass with its surroundings as it rises. This is shown in the figure on the right. This adiabatic expansion results in the cooling of the air mass as it goes higher in elevation. Now that we've described the conditions that must exist to form a thunderstorm, we can define the life cycle of an ordinary thunderstorm in three stages. The first stage being a development stage, where warm, moist air is lifted to an altitude at which it becomes buoyant. Second is the mature stage, where ice particles in the lifted clouds fall downward into the warmer air, melting into raindrops, pushing air in front of them and producing a downdraft. Finally, there's a dissipation stage. The downdraft formed during the precipitation suppresses the updraft and shuts off the source of moisture in the storm. The progress of this life cycle is shown in the figure below. This may be slightly out of place, but it is interesting to know that when a cloud or a thunderstorm cloud rises to the top of the tropopause, the top of the cloud spreads out onto a flat layer due to high altitude winds that spread them laterally. This makes the cloud's shape resemble a classic blacksmith's anvil. We'll go on to describe a few different types of thunderstorms, the first being squall-line thunderstorms. These form along a distinct line that marks the edge of a type of front or a gust front. As individual storms merge, they form a large cold pool at the ground that spreads out, which forms large gust fronts and triggers the formation of new thunderstorms. So this is the development of a squall line thunderstorm in figures in the figures below at times A and B. We see they're isolated at the beginning and coalesce at the end. This picture shows a frontal squall line along a cold front within a mid-latitude cyclone. We'll discuss mid-latitude cyclones later. Supercell thunderstorms are thunderstorms containing particularly strong, long-lasting, rotating updrafts. These are shown in the figures below A, B, and C. The development of a supercell is somewhat complicated because it involves a decent amount of mathematics and physics describing forces like torque and shear. However, we'll go in a broad description of the development of a supercell. So in time A on the left, you have wind shear causing low elevation air to swirl around a horizontal axis. So we have the high elevation wind in purple running across and above the surface wind, and that's producing a rotation that shown in the sort of curled horizontal column below them. In time 2 or time B, updrafts arch this tube of horizontal air upward. In time 3, rain produces a downdraft which changes the shape into two arches that split. This will be on the picture on the left. And then the two storms may separate in the picture on the right. So you can see with the arrows we've created an updraft, which is the red arrow, the air moving up, and then the downdraft, the blue arrow, the air moving down. You may tell from this description that in order to understand in detail these supercell thunderstorms and storm development in general, you must try to think in 3 dimensions. The word mesocyclone describes the counterclockwise rotating updrafts of supercell thunderstorms. So in this figure, you're seeing the mesocyclone in the center, and then the cold front, or gust front rather, with the triangle teeth on the bottom right. You're seeing differences in the amount of rain in different portions of the mesocyclone. Finally, you'll see the location of updrafts and downdrafts. Now I'll discuss lightning. Lightning is a large electrostatic discharge caused when a negatively and positively charged particles become separated in clouds of a thunderstorm. There are 2 main types of lightning, which are cloud-to-cloud lightning and cloud-to-ground lightning. Cloud-to-ground lightning can be formed in 2 different ways, where negative polarity from the cloud reaches positive polarity ground, or positive polarity cloud reaches negative polarity ground. No matter how this occurs, lightning always produces thunder. The top 2 figures show something called a stepped leader that descends from the cloud while a positive streamer rises from the ground below. In this case, we have negative ions from the cloud reaching a positive ions from the ground. When they connect, it creates a return stroke that makes the lightning flash. In this case, because it is stepped, we see sort of dendritic pattern or fingering-like pattern of the lightning strike as a result of the strong distribution of negatively charged particles coming from the cloud. The bottom 2 figures show a dart leader descending from the cloud while a positive streamer flows upward. In this case, when the second return stroke flashes, it produces a single lightning bolt. So this pictures show the difference between a stepped leader and a dart leader. Lightning can be extremely hazardous. It can cause trees to explode, ignite flammable materials, blow out electrical transformers, and permanently harm or kill persons or animals that it strikes. Another hazard of thunderstorms are downbursts. These are outrushing winds from strong downdrafts, eventually become straight line winds that can travel in front of a thunderstorm at high velocities. So this picture shows a downburst that may produce a headwind or a tailwind depending on the location of the plane relative to the direction of the wind. Hail is another hazard of thunderstorms. It is a spherical or irregularly shaped lump of solid ice that forms at a high altitude during a thunderstorm and precipitates down to Earth's surface. Tornadoes are violently rotating funnels or vortices of air that extend from the ground up to the base of a severe thunderstorm. These can be especially dangerous. For example, the image on the bottom left shows a tornado track or path of destruction that the tornado has left on the ground surface. This is taken from a false color satellite image. On the right is a series of tornado tracks from Tuscaloosa, Alabama in April 2011. These show the concentration of the tornadoes, the distance they've covered, as well as their different destructive strengths as noted by the EF scale and their colors. Similar to the formation of supercells, the formation of supercell tornadoes is especially complicated, but we'll explain it. Supercells contain strong rotating updrafts called mesocyclones and have strong downdrafts on the forward and rear flanks of the supercell associated with heavy rainfall. Picture on the left, we have the anatomy of a supercell with updrafts and the storm movement to the right. On the right, we have strong winds that cause the updraft, red arrows, to tilt. Both forward flank and rearward flank downdrafts develop as a result of this. In stage 3, the boundary of the rear flank downdraft forms a horizontal roll of rotating air close to the ground. In stage 4, the part of the roll under the updraft gets drawn upward and tilted into the updraft. As it stretches and thins, it spins faster. Finally, in stage 5, the air roll tightens into a tornado and protrudes from the base of the wall cloud. So you can think of this roll being like a rope that gets caught up in some wind or whipped around, eventually snaps off and forms its own tornado. A few slides ago, I mentioned that we can measure the strength or intensity of tornadoes based on a standard scale. This is known as the enhanced Fujita scale, and it's currently used to classify tornadoes based on the damage they cause, and it's used to estimate wind velocities. So the scale runs from 0 to 5, with winds starting at 65 miles per hour and ranging over 200 miles per hour. 5 being the most damage, catastrophic damage that can cause buildings to collapse, severely damage reinforced concrete, and carry cars and trucks for long distances. Here are some pictures showing the aftermath of tornadoes. There's an area where tornadoes form in especially high numbers every year. This is known as Tornado Alley in the Midwestern United States. In this case, this is where warm, moist air from the Gulf of Mexico collides with cold air from Canada, producing the largest number of tornadoes. This is shown in the figure below. Now we'll move on to the third part of the lecture, discussing mid-latitude cyclones and tropical cyclones. Mid-latitude cyclones are huge swirling masses of air that develop between 30 and 60 degrees latitude. Cyclones swirl counterclockwise and anticyclones swirl clockwise. These grow into massive storms that cover large parts of North America. In order to understand mid-latitude cyclones, we need to first discuss some terminology known as high pressure centers and low pressure centers. High pressure centers are cold, dense air that converges at the top of the troposphere and sinks down to Earth's surface where it diverges from the center. Low pressure centers are just the opposite, where air converges at a lower pressure center and then rises up to replace the colder, sinking air. High pressure centers are created from a phenomenon called convergence, shown in the figure on the left. In this case, we've got high altitude air traveling to the right in our diagram. The faster air is on the left side of that diagram, and the slower air is on the right side of that diagram, which produces something like a traffic jam at high altitudes and pushes cooler air downwards. This is known, again, as convergence. Divergence is just the opposite and produces low pressure centers. In this case, in the diagram on the right, we have slower air on the left side and faster air on the right side moving at high altitudes. In this case, we get a divergence where the slower air cannot keep up with the faster air, resulting in empty space. In this case, warm air rises to fill that vacuum and produces a low pressure center. Now let's discuss how mid-latitude cyclones form. First, air initially flows upward over frontal boundaries. On the left side of the top diagram, we have a cold front, and on the right side of the top diagram, we have a warm front. Remember, in cold fronts, warm and cold air are moving opposite directions to one another and colliding, whereas in warm fronts, the cold and warm air may be moving somewhat in the same direction. This diagram doesn't do the best job of showing it, but it is important to recognize. In the diagram, the second diagram, the cold front advances southward and eastward around the center of low pressure. So in this case, we've got one of the cold fronts that's starting to move and advance in a anti-clockwise pattern, rotation, around the low pressure center. At time 3, the cold front reaches the warm front because cold fronts move faster than warm fronts. And then at time 4, the cold front overtakes the warm front, which creates the occluded front that we discussed at the beginning of this lecture. In mid-latitude cyclones, there are strong pressure gradients, which create strong winds. This produces blizzards, tornadoes, and strong thunderstorms. Convergence and uplift produce broad areas of cloud cover and precipitation as well. A mature mid-latitude cyclone is a comet shape shown on the right and can bring a variety of different weather over a broad region, like thunderstorms and blizzards. Additionally, a mid-latitude cyclone acts like a complicated series of conveyor belts, bringing warm air northward, cold air southward, high altitude air downward, and low altitude air upward as the fronts evolve. Now let's discuss tropical cyclones, which are rotating spiral-shaped storms that originate over warm tropical ocean waters and include hurricanes and typhoons. The Saffir-Simpson scale is used to rate hurricanes based off of their maximum sustained wind speed and includes categories 1 to 5, which Floridians are certainly familiar with. Category 5 has winds greater than 150 miles per hour, with total catastrophic damage occurring. This slide shows the internal structure of a hurricane. Well-developed hurricanes have distinct eyes, eye walls, and spiral rain bands, moving from the center outwards. Hurricanes only form over warm water with temperatures greater than 26 degrees Celsius or 79 degrees Fahrenheit. A cluster of different thunderstorms can act as a seed for hurricane development. Rising air must condense and then release latent heat, which further warms the air, causing additional rising air and further condensation. As the storm moves off of the equator, the Coriolis force causes rotation. If upper level winds remain weak, the spiraling circulation of the hurricane can remain strong. So the figure below shows the development of the hurricane near the equator in the Atlantic Ocean. Hurricanes are known to cause lots of damage to human life and property. One way that they cause damage is through storm surge. Storm surge is the dome of water that forms in front of a hurricane. Storm surge occurs when wind and low atmospheric pressure combine to produce a large bulge of water coming from the ocean and crashing over landscapes. Hurricanes follow predictable paths based on prevailing wind patterns, although predictions decrease in accuracy the further in time they extend. So below are some typical hurricane paths of Hurricane Dorian in 2019. On the right is the actual path of Dorian, showing a slight difference.